3. Although we've managed to find an elegant synthetic way, and we showed that the product has beneficial properties such as solubility and stability, that means nothing if not for wanted reactivity. And we set ourselves to test its reactivity. And how we did that? We took imidazolium fluoride and reacted it with metal tetrafluorides, namely silicon tetrafluoride and germanium tetrafluoride, to obtain discrete Trigonal-Bipyramidal pentafluorido silicate and pentafluorido germanate anions respectively. And then you can take the formed product, react it with additional equivalent of the reagent, and the reaction yielded us hexafluorido germanate anion. Now, here are the crystal structures. This is pentafluorido silicate anion. This one is not as interesting because there are about a dozen such structural motifs reported in the literature. However, this is the first example of structural characterization of pentafluorido germanate anion. And I would like to spend the last minutes to talk about the surprising fact that we managed to stabilize and crystallize this product. If you think about it, the chemistry is not that hard, really, and it's not like we are the first that tried this. There were several reports that tried to perform such a reaction with different fluoride sources, but none of them achieved the isolation of discrete Trigonal-Bipyramidal pentafluorido germanate anion. And if we take a look at the crystal structure, we can see that metal halides tend to form hexahalidometallate anions, and pentahalidometallate anions represent only roughly 10% of all the structures. And we were wondering why. And in the literature you can find and perform calculations. So for example, you can calculate, if you want addition of one fluoride to, let's say, germanium tetrafluoride to yield pentafluorido germanate anion. And if you then calculate the total energy of this system, you see that the product is favored against the reactants by roughly 340 kilojoules per mole. And you can then calculate the next step, so addition of another fluoride to pentafluorido germanate anion to form hexafluorido germanate anion. However, if you take a look, this one is disfavored to the reactants. And so this model does not appropriately address the empirical data and the observed structures. And then we turned for help to a brilliant mind of Tone Kokal, and he said, of course this is so. These are isolated anions, and germanium as a small object can hardly accommodate a large surplus of electron density. But in reality, these anions are never alone. They are always surrounded with cations for the purpose of charge neutrality. And we said, why don't we devise a new, different theoretical model where we have all molecular species. So we have molecular sodium fluoride, germanium tetrafluoride, and the corresponding products. And if you then perform calculations on this system, you can see that they reflect the observed structure, the empirical data. Namely, the first product, so sodium pentafluorido germanate, is favored against the reactants by roughly 180 kilojoules per mole. However, the next reaction step is even more favorable. And although these numbers are not to be taken too absolutely, it was the trend that we were interested in. So now we had a model that shows us the state of nature, and what you can do with this model then is you can change it with different cations. You get different values, and you can then deduct these values to get a difference. And this difference now gives you information how much is pentafluorido germanate favored or disfavored against the hexafluorido germanate. And we did this. You already see the numbers for sodium cation. The difference comes to minus 63 kilojoules per mole, and we collect the number. We did then the same for ammonium cation, which is slightly bigger, and collect the number, and in the final step we did this for tetramethyl ammonium cation. And now we have some absolute numbers that, again, don't tell us much. But what you can do with these numbers is you can plot them as a function of the distance between center of charge of the cation and center of charge of the anion. And if you do this, you can see sodium as a really small cation can get really close to the anion, and the energy difference is quite negative. Ammonium, slightly bigger, cannot get as close. The energy difference decreases a little bit, and in the case of tetramethylammonium cation, it comes up to the positive values. So now what this tells us is that thermodynamic preference of hexafluorido germanate against pentafluorido germanate diminishes with increasing size of the cation. In other words, small cations can effectively stabilize more electron density on a given moiety via electrostatic Coulomb interactions. And here a PhD student asks himself, aren't there a lot of systems that are driven by electrostatic interactions? And so the question here arises, how could these results be viewed or expanded to biological system, drug design, design of materials, self-assembly, etc. All systems that are heavily driven by non-covalent interactions. And we're not saying that in our case this is absolutely true, because right now we don't have, we have no way of knowing. But it may as well be that the specific bulkiness, the specific characteristics and geometric properties and electronic properties of our cation increased the crystallinity in our product that enable us first structural characterization of pentafluorido germanate anion. And I would like to conclude this part 3, that we showed successful reactivity of our novel reagent. We isolated discrete Trigonal-Bipyramidal anions. We showed the first structural characterization of pentafluorido germanate anion, and devised a new theoretical model for relative stability assessment of pentafluorido germanate versus hexafluorido germanate structural motifs.